Hey, Dr. Clark here, and in this main idea video, we're going to be looking at Dirac delta forcing or impulse forcing and how it interacts with the Laplace transform. Let's take a look. So, to give you an idea of what we're looking at with Dirac forcing or impulse forcing, imagine a spring mass problem that's tapped with a hammer. So, you've got this spring mass kind of oscillating back and forth, and then after 3 seconds, it sort of gets tapped with a hammer, which is going to sort of instantaneously change its velocity. And the way you could see that sort of in a as the solution is, maybe initial position is 4, it's going down to 0 because it's overdamped, and then at 3 seconds it's tapped with a hammer, so the velocity is instantaneously changed, and it starts going back up again, and then coming back down to 0, right? The notation we would use is this Dirac delta t minus 3 to indicate that it happens at 3 units. And the 2 here is indicating how hard we hit it with the hammer. If it's 2, it's going to change the slope by 2 units. That's sort of the key idea with Dirac forcing. But just writing symbols down doesn't really do anything for us. We need to actually understand that mathematically. So what is this? Conceptually, it's hitting a spring with a hammer, changing its velocity instantaneously. What does that mean mathematically? So the way we get at it is you can imagine that the Dirac force at t equals t naught is sort of a limit of these fh functions as h approaches 0. And what these fh functions look like is it's a width of h, so it starts at t0 and goes until t0 plus h, but the height is 1 over h. And if you multiply h by 1 over h, you always get 1. So there's always a unit 1 mass here, if you want to think of it. But as we shrink the h from, say, 1 to 1/2, the height is 2. At a quarter, the height is 4. At a tenth, the height is 10. And so the area under the curve is always 1. But as h shrinks smaller and smaller and smaller, that force gets stronger and stronger, but over a shorter and shorter amount of time. So the total net acceleration is sort of constant at 1 unit, but the time in which that acceleration occurs is shrunk down to 0, and in the limit becomes actually 0. And so this Dirac function is really the limit of these. But what the Dirac function is sort of, you can imagine it to be a function that's sort of 0 everywhere and then infinity at a single point and then somehow carries with it an acceleration. Well, that's not going to make sense as a function, but it does make sense as a functional. And if you take more advanced math classes, you can learn about functionals. What we're going to do is sort of understand it via the Laplace transform. Okay, so how would the Laplace transform interact with this? Well, we can certainly take the Laplace transform of the fh function, this constant function between t naught and t naught plus h. And in fact, if you do that, when you integrate from 0 to infinity, you're only going to integrate from t naught to t naught plus h because everywhere else fh is 0. The height is 1 over h on that interval. And then this is really just integrating e to the minus st. So you get negative 1 over s, e to the minus st, evaluated from t equals t naught to t naught plus h. When you plug those values in, you get this expression here. And using the laws of exponents, we can factor out e to the minus st0 out to the left-hand side here. And I'm going to write the h in the denominator with the remaining part here, which is e to the minus sh. And this will just be 1 when that's been factored out there. And then, of course, h in the denominator. And then what we want to do is take the limit as h approaches 0. Well, if we take the limit as h approaches 0 for just the function, we sort of get something that doesn't make sense. But we could take the limit as h approaches 0 of this Laplace transform. And that's what we're going to do next. So when we do that, essentially these are just things in terms of s's, so they aren't affected by the limit. And then we use L'Hopital's rule because this is type 0 over 0 in terms of h. So differentiating the top and the bottom gives you 1, 0, and then a minus se to the minus sh. As h approaches 0, this just becomes 1, and so you just have minus s here, which cancels that minus s. And so the limit as h approaches 0 of the Laplace transform of fh is just e to the minus st0. And so essentially, for any t naught bigger than 0, the Laplace transform of this Dirac delta function is defined to be e to the minus st0. And you can make this more precise mathematically in advanced classes, but that's going to be essentially anytime we see Dirac delta and we hit it with Laplace, we're going to get e to the minus s t naught. And the t naught is, of course, where that Dirac delta occurred at. So that's the main idea of this section, is we can do impulse forcing. The way we do impulse forcing is using this Dirac delta function. And while that isn't really a function, it is the limit of nice functions, and we can take the limit of the Laplace transforms to get essentially what would be the Laplace transform of that Dirac delta, and the answer is e to the minus st0. So if you recall back to that second translation theorem we had before, e to the minus st0 shows up a lot when you have these shifted and turned on functions. So remember that if you shift a function and then turn it on at a particular value, when you Laplace transform that, you get this. Well, if we're going to be getting e to the minus st0 from Dirac deltas, then we're going to need to inverse those kinds of things. And so what we're going to get is these shifted over Laplace transforms. And so that's really what you should imagine going back to this. What's happening is you've got the original function, and then you've got a new function that starts at that point, basically, and it's just shifted over. And so that's how it actually gets applied mathematically. Let's take a look at an example of how you might do this for a complete problem. So here we've got an initial value problem. We've got a Dirac forcing at 2 with a unit of 5 there, so it's going to probably change the slope by 5 units. Initial position 3, initial velocity 0. And it's second order. It looks like undamped though, so I should be expecting sine of t, cosine of t as my homogeneous solution. All right, and this is in fact what the solution will look like. You can see we start out with a sort of a cosine type function starting at 3 with initial velocity of 0, and it's going to come down and oscillate, and if nothing happened it would just oscillate forever. But at 2 units we hit it with an impulse force. It was moving sort of to the left, and it gets hit with a hammer, and now it's moving to the right, so the velocity changed by 5 units all at once. And now it's bouncing up there, and now it's going to continue on. Well, it continues to be undamped, so it's just going to continue on as a sine or cosine function from that point on. So that's sort of what we expect to happen theoretically. Let's see how you would actually solve it. So what do? You start with your differential equation. You hit it with Laplace transform. Of course, L of y will just be L of y, and L of the second derivative of y, well, you're going to use that first derivative formula, so you'll get S L of y minus y naught, or y prime naught, which will be 0. Then you'll hit it again, and you'll get S squared L of y minus S L, or minus sy of 0, which is 3. So that's where that 3s comes from when it's added to the other side, and the s squared there from the characteristic equation, basically. And then what happens to 5 delta t minus 2? Well, we know the Laplace transform of delta is e to the minus t naught s, and since t naught is 2, we just get e to the minus 2s here with the 5 on there from the linearity property. So we're going to factor out the L of y's. That'll give us s squared plus 1, which we divide onto the right-hand side, and we get 2 terms is equal to L of y. All right. Now, if you think about what these terms are, this looks like coming from cosine. So that's probably going to be, what, 3 cosine of t? Which makes sense. If you ignored right-hand side, you'd have 3 cosine of t would be the solution because it initial position 3 and initial velocity of 0. So that's exactly what we're going to expect from here. And then this is coming from the Dirac mass. So it's that e to the minus 2s times what looks like a sine function. And so what's going to happen is we're going to get a shifted sine function. So when we apply the inverse Laplace transform, we do in fact indeed get 3 cosine of t from this. We'll get 5, and then we'll get sine of t, but it's going to be shifted by 2 units. So it's going to be sine of t minus 2, and then multiplied by u t minus 2. U is that unit step function, so it's going to be 0 up until 2, then turn on and become a sine function. And of course, if you look back at the graph, there you go, there's your 3 cosine, and then it changes velocity by 5. Of course, a 5 sine makes sense because sine has position 0 but velocity 5. So the velocity instantaneously changes by 5 units starting at t equals 2, and there's your solution. All right, so that's kind of how you solve one of these things. It's very similar to what we've done before. We just add another thing to our list, which is the Dirac delta. How do you Laplace it? And that ends up on the right-hand side. And then when you solve back with the inverse Laplace, what usually happens is you have something like e to the minus st naught, and that's going to be a shifted function with a unit step function to turn it on at that particular time. So that's going to happen over and over and over. Look ahead to the next couple example videos if you want to see some more examples, but that's the main idea of how this works with Dirac delta forcing. So I'll see you there.